For some reason, what have we messed up here? There we go. Right. Rightio. Hey, good morning, Lydon. Good morning, Deft. This is the last stream, by the way, at exactly this time, because we go onto daylight savings time in the morning tomorrow. So it will be an hour earlier in terms of GMT, and I think for those of you in Europe and the like, many of you will be falling back off of summertime very soon, so it will start moving. So yeah, hey, welcome along to Serious Limbs, Noop, Raffy, and others that are lurking along. So, and Codex we. MCWP says, I wish they did daylight savings here, seriously. Because you're up in Queensland, are you, I think? Is that right? Yes, you are in Queensland, aren't you? So, yeah, it's, well, as we know, it's the paranoia over fading the curtains and upsetting the cows, right? I actually just wish that we just stayed on summertime the whole year round, right? So then in the winter, you at least know that in the evenings you have still some decent daylight. And, you know, who cares if more of the year that it's dark in the morning. But anyway, let's have a look at floppy things. So I need to do that so I can see what I'm doing. So MVP's asking, cows don't make it home. No, it's not like cows don't make it home. So this was going back to the Joby Peterson days. Was when we, for those who aren't Australians, when we had a police state in Queensland, effectively. And the farmers were complaining that daylight savings, which was practiced at the time, if I remember correctly, was upsetting the cows because the cows were changing what time they had to get milked. When the farmers should have just kept to the same time that they're farming the milks and milking the cows. It's not early in the morning, and yeah, causing dramas. So, but back to the floppy thing. So let me, I don't know. Hopefully that's big enough to read. I'm just going to paste into this a little bit of info from. So show you what we're trying to beat. So now that we have the RLL floppy stuff working, RLL, that's a RLL 17 code. This is what we want. RLL 27 code. Pasty. Let's just get this. So I can see what you guys are talking about in the back rows. So, for those who are not familiar with how floppy encoding works, actually what I should do is put the, so that MFM is equal to an RLL 1,3 code, and it's a half rate code. RLL 2,7 is also a half rate code, so it doesn't sound like it should be able to put more on the disk. But the trick is, if you this is what gets written to the disk. And what you'll see is there is always at least 2 zeros. Oh, yep, sure. Lighten23 just pointed out that the music's still a bit too loud. Is that better? Again, let me know if it's not. I'll knock it down one more just to be sure. There's always at least 2 zeros between a 1 within the code. And if you stick any of these next to each other, that always holds, because in fact actually all the codes have got 2 zeros on the end. So if you put them one after the other on the disk, I'm doing well this morning, aren't I? They will always have at least 2 zeros between. And so this is important because the limitation on a PC 3.5 inch floppy drive, I'll put it back up one. And with some music volume, Jeff was just saying that he liked the volume. Hey, Pro7, welcome along. That because there's always at least 2, the PC floppy drives require a certain minimum time between pulses. And when we're talking about pulses, this is the magnetic inversions, right? So the way that RLL 2,7 fits more than MFM is that, hey LGB, is that the pulses are further apart, which means that we can turn up the clock rate and get more pulses per second. It's still a half rate code. So that what the half rate code means, you can see that there's 4 time steps, 4 bits to encode 2 bits. So this is, it's a remarkably efficient code to make a half rate code like that. And so what I've been trying to do on and off for a while is to, like over the last few weeks, to see if I can fit even more data on a disk, is to see if I could go to something like, so the first number in the RLL code is how many gaps there are, right? So I thought, oh, what if I go to an RLL 5, something code? So that would mean there are 5 zeros between each one at least, instead of 2. So that means that instead of there being a pulse in 1 every 3, there would now be a pulse 1 every 6. So we could double the clock rate. That all sounds really good, but I couldn't actually create an RLL 5, something code that approached being a half rate code. Because if it was only a quarter rate code, there'd be no benefit, because we're using twice as many clock ticks, but encoding only the same amount of data per unit time, which is not what we're trying to do. We're trying to cram even more on the disk. So I started thinking, what can we do to try to increase how much we really can fit on the disk? Well, the 2 things that actually matter to us, and we're going to try and quantify this a little bit more this morning, is what is actually the real limit to how many bits per unit, how many pulses per unit time we can do. So how far apart do they really need to be? And what's the resolution once you've reached that point between pulses? So once we've had that long, how far apart do we have? What difference in times can we tell apart easily? Hey Herdware, welcome along as well. So that's what I'm going to try to quantify. What I thought is, well, if we know those 2 parameters, we can actually model how much we can actually fit on the disk. So here is my simple little thing for doing that. So if we say that the minimum gap, so this is based on what we managed to achieve last time in terms of a viable speed for the RLL 2,7. Hey Marauder 64, welcome along. And because it's the RLL 2,3, so it's a gap of 2 ticks, and then there is a tick that has a pulse in it. So it's actually 3 times whatever the data rate is that we had encoded previously. And then I tried to find out what that minimum difference in time is that we can reliably tell apart. And I believe it's about 8 cycles. And that's because I was reading through a TIAC drive manual. So these aren't TIAC drives, they're Alps ones. But we expect broadly similar performance. They indicate a 300 nanosecond margin for when a pulse is red versus when it actually is. So that would be at 40 megahertz, that's about 12 clock cycles. If we use right precompensation, maybe we can knock that down to 175 nanoseconds. Add one extra cycle for safety, and we're talking about 8 cycles. This is a theory. So what I have done here is I've calculated what the bit rate is using RLL 2,7 with those parameters. And what I should actually do is I should parameterize this out. Yeah, it says the disk will go up in flames as usual. That's our hope. So I'll just put here best rate. Best rate int best rate the fastest stable data rate observed for RLL 2,7. Now, in actual fact, we managed to shave it down to 15. So we'll do it with that. And where's my... that looks like a... come on. Right, okay. That'll do us. So here's our program. Now what's that gone done to that? Oh right, okay, that window is wider than my screen, isn't it? Let me... So RLL 2,7 encodes 2 bits in every 84 ticks, because that's 4 times 15 hex. So that gets us a bit rate of 964 kilobits per second. Now remember that a normal 3.5 inch drive with a high density drive will do about 500 kilobits a second. So this is why we're able to cram so much on the disk, right? Is that we're running at basically double the data rate. And we're able to, snip and shave a few other things and cram an extra sector or two on by really filling the tracks up rather than leaving quite a margin at the end. So this is all based on track 0, right? We know that it degrades a bit as we go to the inner tracks. So for comparison, we've said, well, if we imagine that we have a mechanism where we do that minimum gap length that's required for it to be stable, and then we try every different position of the pulse after that, separated by this minimum quanta that we can differentiate reliably, how much can we get on? And I thought, well, this should sound all reasonably optimal. And so we can work it out based on whole numbers of bits, so whether we have 8 different timing positions or whether we have 16 or 32 or 64 or 128. How does it look? Because of course the more we do it with a longer thing, then the more we're amortizing the minimum gap length. But if we have too many positions, then we start, there's a linear cost, there's a super linear cost, exponential cost in fact, that goes up for each additional bit. So there's a sweet spot in there, right? So if we have a look, so if we only want to do 1 bit, so that 15 hex is 21. So 21 times 3 is 63. So it's a minimum cost of 63. that we have in there, and then we have the pulse that we're putting in after that. And I've just realised there's a slight error in this calculation, in that we've charged for the whole quanta, but for the first pulse we don't need a quanta. No, sorry, we do, because for one bit we still have two different positions, so they are a quanta minus one apart. So that would only get us 570 kilobits per second. I'm actually going to quickly change that program so it actually prints the numbers out in kilobits per second. K bits per second. We can just divide that by 3. Well, 1,000. Right? And if I do the same up here for the RLL, right. And I'm just going to, because it just makes my life easier. I'm going to try and get the things to line up. And so we want to move them 1, 2, 3, 4 further over, just because we're going to be looking at these things repeatedly. It's just going to be so much easier if we have a nicely aligned table. Right. That all looks nice and tidy. Definitely currently flashing the first stable bitstream ever. Yes, because we now have a process for doing stable bitstream releases, which is fantastic. It's been a while. The master branch is now up to date on the MEGA65 core, because it had been languishing behind for a long time. Right, so back to torturing disks. 964 kbits per second is what RLL 2.7 gets. If we go to 1 bit, so that drops down. If we go to 2 bits, and now we have 4 different timing positions that we have to encode, we approach, in fact, what RLL 2.7 does. And if we do 3 bits, and now we have 8 different timing positions, we can actually beat it. Yay! This is great news. Not by very much, is the thing. And once we go to 4 bits, it all starts looking all very sad and miserable again. We start dropping down below. So, yeah. Okay, Retrocombs is saying, not sure if you've seen the chat on Discord, but the speculation that all the work to pull extra capacity is based on ALPS drives. I can't imagine that's the case, but I thought I would ask. Yeah, so I'm using an ALPS drive, so it might be that what I'm doing, some of this will have to detune slightly for other drives. I have piles of other 3.5-inch drives of different brands here, but I think we're going to find that their performance is very, very similar. I'm not particularly worried. And in the worst case scenario, we could probably find a way to get ALPS drives for those 100 folks. But I don't think it's going to come down to that. So yeah, should be fine. Anyway, so back to what we're doing here. So these should be achievable rates. So we can see that there is a slight improvement. I just need to shut the door again so I don't wake anyone up. So Herdware is asking how many of those ALPS drives did we get. The Mega strategic stockpile of 3.5-inch floppy drives is certainly more than the 1400. So yeah, but we need to figure all of that out, and we'll know the answer to these questions as we kind of go along as to whether we need to even worry about that or not. Essentially, any late model 3.5-inch floppy drive should have quite good performance similar to these ALPS drives. It's the bad old days of the ones that have the 12-volt motors that had much more problem with the reliable spin rate of the disc, and that is the fundamental limit for this. That having a very stable spin rate is what's going to enable us to get more data in, because that minimum quantity that we can discriminate between, if the drive doesn't have a stable spin rate, that goes up, and then that means that we can get less on there. So as an example, if we, so this is the nice thing with having this is a nice little model, right? So if we said instead of the minimum quantity being 8, if we make it 10, you see we actually can't beat, that no longer beats the RLL code. Now, this is just by varying the position of a single pulse. We can get smarter than this, and so that's the next thing for us to look at. Is because let me if I which right. So if we imagine for a moment that we have a code that requires 8 spaces, and then we can stick a pulse on the end, right? So what we're talking about for a code at the moment is doing something like this. So we're changing the lengths. Now what we're also doing in this simplification of the code is that we're making them all a constant length, because if we have a variable length code, life gets hard. The RLL code is really clever in that it looks variable length because there are bits of different length, but the number of bits that get encoded per unit length doesn't change. Now it turns out to make an efficient code like that, I've tried over the last 3 weeks, I can assure you, I haven't been able to make a longer code that has that property, because the longer that initial gap, then the longer these things end up, and the longer the code is after the gap, the more that you can encode. And so if we imagine for a moment that we had, well, if we look at the RLL 2,7, right? So it has to be at least 2 zeros between each thing. So I'm putting it at the front rather than the end just because it's a little bit easier to kind of look at. So that would be a valid code. We'll just do the minimums for the moment, right? But that would also be now a valid code, right? So, but we can also do, so if we say we can't do that, if we go for 6-digit codes, so they would all be valid codes. So we've now got 3 different possibilities at length 6. And let's look at a length 7 code. So again, we have to keep the rule of having at least 2 gaps between each code. So they will all be valid. We can also do that. We can also do that. We can also do that. And that. So you can see we've now got 7 different codes that all meet the criteria. Now, if we had 8, we would be able to encode 3 bits doing this in only 7 clock ticks. Now, remember that the RLL 2,7 code, the blasted thing, is a half-rate code. So this is not a half-rate code because it uses on average more than 2 ticks per bit encoded. So this gets almost 3 in 7 positions. And so if we actually went to, if I do for argument's sake, we'll do one that can fit more in. I think it's Marauder is saying I noticed that some 3.5-inch drivers don't have the same pinout, so I tried to see if I had a spare for my M65 dev kit, but the physical connector on one of my spares, a Mitsumi 3.5-inch driver, would not fit. I think some of these were designed specifically for PCs which don't use some pins. The connector was missing almost a whole row of pins. That should actually be fine. The drive should still work, because lots of those extra pins are ground pins. And I'm just having to see whether there's anything else in chat here that folks were covering. Sorry, hear a noise outside. I think it was my son rather than possums running around on the roof. We get possums. We've got a roller garage door, one of these ones that kind of rolls up into the thing, and that's prime possum real estate to live in. The problem is that the possums like to sleep in there and then they die. Possums die where they sleep. The stupid things. And then they stink really bad, and they often die in summer when they get a bit heat stressed. And then they basically just, we just then have this possum rotisserie that just, and then dead possum bits fall out the ends occasionally. So, yes, keeping an eye on the possums in there. Anyway, now back to the more interesting stuff. So with let's do all the codes that we can. That would work here. So again, we can do it without the extra pulse. So now let's do the ones where that's in that position. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 codes. So that means that we can do 3 bits. We don't have 16 codes, otherwise we could do 4. Length is 8. So 3 bits over 8. So that's a 3 on 8 code, which is less than a half. So doing it this way, and this is all the possible codes, right? So that RLL 2.7 code actually gets better than what you would think is possible, because it gets all clever pants with the way it handles those short codes and being able to glue them together. I have no idea how the people came up with that, and I have no idea of a way to procedurally generate longer codes that are that clever. If someone has an idea and can show me a longer code, so it has to be one that has a longer minimum gap than 2, but that can still be a half rate code or better, because with longer codes you can in theory actually exceed half rate for a code. Tell me, because that will actually let us fit more on the disk. So forget the spiral challenge. Try and come up with codes that satisfy some criteria. Like for example having 3 gaps between the pulses that can fit more in there. Herdware says many years ago some people had a lot of falling down in their inner walls and dying when it was like 25 degrees. Very fun to try to air that out and still living in the house. Yes, so that's opossums. So remember, so similar name, small, LBJ, little brown job kind of animal kind of thing. Genetically actually very different, because your opossums aren't marsupials. Ours are marsupials, and but anyway. So yeah, if anyone can come up with a better code that has those properties, I'd love to hear. But what we're going to do instead is this style of how many different things can we pack in a solid. It's a constant length code here. Yes, Deft is saying to avoid the possum problem, try solid walls. Yes, that's a good idea. One of the other things that possums are great at is getting into your roof somehow. So if you have a gabled roof, they'll find their way in and then they'll die and stink. And then if your ceiling's not very good, they'll dribble possum putrescence. as they decay if they haven't mummified properly. Yes, that's right. Yeah. So M3W says, we had that in the roof and it bloody died. Yes. So our house has been extended a couple of times. This is common here in Australia. And between two of the extensions, there was this gap, kind of about yay size, about 2.5 meters long, 3 meters long. So this was perfect possum real estate. They used to fight over it endlessly, and yeah, they'd live in there and they'd die. And then because it was where the two extension parts of the house joined on, it wasn't completely smell tight, and that was miserable as well. Yes, yeah, so definitely saying, sure, we got animals coming there too, but they get out again. Yeah, so it's a particular thing of marsupials that they love to sleep. Sorry, to die where they sleep. So if they're not feeling well, they go back to their safe sleepy spot and die. So it's different to cats, right? So cats and all the feathered things like to go away from where they live when they feel sick, and so they tend to die away from where they've been living. So I think the same goes for the mustards as well, right? Because they're basically stretched cats. So Faro is asking, is this Huffman coating or something like it? No, so Huffman coating is variable length based on probability. But Huffman coating doesn't have this requirement that the pulses be a certain distance apart to satisfy the magnetics. So you can kind of think about it as, it's a constrained code, and you're trying to make an optimized constrained code. Back to the point at hand. So if all we do is like up here, right? So we just change what the time is between the pulse, and we're stuck with constant length, right? Because you can see if it's not constant length, we can actually get more codes in somehow. But we can get some of those extra codes in by doing... hey Anton, welcome along as well. By having multiple pulses in the thing. So if we wanted... So in this case... Oh, hang on. No, there are 8 codes on that one, right? So that's 3, 4, 5, 6, 7. I'm sure I considered that code. So that's 8 codes. Gets us 3 bits. Length is equal to 7. So this is a 3 on 7 code, which again is still less than the half rate code that RLL 2.7 manages to get. So Skazlin is saying, is this like GCR codes in the 1541? Yes, it is similar. Now the difference, the 1541 doesn't have this limitation that there has to be gaps between the ones. Its problem is you can't have too many ones in a row. So different drive types have different magnetics with different limitations. They all have some annoying magnetic limitation. But the type of limitation varies quite wildly. So, but anyway, so we can, with this system that I'm, my little modeling program, we can describe these kinds of codes. If we want to do these codes, we need something that can procedurally generate each of the codes so that we can verify how many there are in a given length and determine the minimum length that gets us the sufficient codes to do a certain number of bits. And that also needs to be easily procedurally generated, because we're going to have to, in FPGA, be able to, given a bit pattern, turn it into the code, and given a code, turn it back into the bit pattern if we want to actually be able to use them. So that's the next little piece that we need to work on. So that's what I started up here with this ID to bit stream. So the ID is the bit sequence. Why don't you just call it index instead, right? And positions is the code length. So if we do it that way, hang on, is that, no, so positions here is actually how many different positions after the initial gap that we have. So we start by putting the minimum gap on the front, and we know the minimum quanta that we need after that. I'm saying, isn't the limitation no more than 2 zeros on the 1541? You might be right. I can't remember. All I remember is it's not a minimum gap between transitions. It was a different rule, and you could have transitions much. Like every clock tick, you can have a transition. Because it might be that the 1541 is directly encoding magnetic orientation with bits, whereas on these drives, it's a flux reversal is a 1. And a 0 is no change to that. Okay. Sorry, just hang on a second. My son's asking me something again. Right. Faro's just posted a link into the chat with a video talking about how the 1541 does it, which I might actually have a look at later. Let me get that link for reading, just for my curiosity. Okay, so back to, hey Judge Rock, welcome along. Right, so we want to procedurally generate all of these things. So I'm going to let's do a little loop just to test this out, right? For int what do we, index, right? Just copy the function prototype down. So positions, and we'll work, so min quanta we know, right? Min gap we know, and index we know. So positions, so what this is, so if we, in fact I'm calculating it up here, right? So positions is how many positions in that, in one gap time equivalent can we have. And so what we're trying to work out is how many positions before we can put 2 pulses in, right? So if we come back and look at these codes, right? So we know that we can put 1 pulse every 3 ticks. So we have effectively 3 positions that we can put a bit in, if you like, in that time. Now what we have to do is we have to watch out that we don't have a collision where they come in. So the positions here we would say is 3. So we want to generate codes that are all valid, but that we can deterministically transform through. So let's because I've changed it to index, haven't I? And excellent, we've got a segmentation violation, because what we need to do is terminate that string, right? And we need to return it. That would be really helpful too. Right. And we still have a segmentation violation. What did I set maximum bit length to? A large number. Oh, yeah, duh. Helps if I actually supply the right. Right, so that's trying to do crazy stuff. Because this loop is not exiting because we're dividing that and adding 1. I'm just going to do that. Okay, so this is clearly not actually doing what it should do yet, but what it's doing is it's producing that initial gap at the start. What I'm going to do to make our life easier to look at this is we're just going to pretend for the moment that our minimum gap is 8. And that our minimum quanta is 1. So this is just going to produce much shorter codes, right? Oh, yep, Codex we said, yes, printf missing arg. Yep. Excellent. And Forrest says, it warms my cold, dead heart to see Emacs. Yes. Right, so let's now try and put these things in. So what we should be doing, so the digit, so this is within that position, we're working out where we're putting it, right? So we want to, for I is equal to 0, I is less than digit I plus plus, bit stream offs. So we need to put the leading zeros in, then we need to bit stream offs plus plus is equal to a 1. For int I is equal to digit plus 1, I is less than positions, stick the zeros on the end. Let's see how that looks. And yeah, I've left off a thing, haven't I? Okay, so that's beautifully producing bit patterns, which is great. Let's and so the good thing, notice that if we were doing this naively to do 128 things, from after the first 8 zeros, we would be having another 127 digits. So this is all about making these Adan sites shorter so that we have a chance of getting better performance out of them. I wish that there was a way in the web version of the Twitch client that I can have it beep when you guys chat, because it doesn't tell me when you guys say something, which is highly frustrating, but I can't see a way to fix it. If someone knows how to do that, let me know. Would love to hear. Right. What I'm going to do, just so that we can see better what's going on, is I'm going to put brackets around each of these things. So we can see that in each of those bracketed areas there is not more than one pulse and they're in different positions. Now what we can see here, we have a problem, right? Which is it's currently allowing an invalid positioning of them, because what we actually have to do is we have to pad this actually out to a full gap length after the gap, so that it can't result in those. So we actually have to have a long gap after that, and then we can have the bit in any position. So now that you can see the code's a variable length now, so this is not necessarily a problem, but we have to again be able to generate codes of a fixed length using this kind of thing. So let's actually have a look at how it's generating them, right? So first code, okay, so that's not valid, right? Because so index 0 we're actually not going to allow, by the way, which I'll actually fix by just saying index plus plus. We have to include at least one bit, so we shift the index numbers by 1. Right. So that's all fine. Yes, the processor saying, maybe you need a bang listen like Shannon has. Yeah, that would be great. That requires the Windows native client for Twitch, because he's running Windows, so he can do that. So I had a look, and there is no Linux client. It tries to run under Wine, but doesn't actually draw anything on the screen. So if anyone has a solution for a better way to control Twitch, and to access the Twitch chat from under Linux, I'd love to hear that as well. Okay, so now what we need to do is to figure out why it's always having at least 1 0 on the front of that. And we need to figure out how we are going to do the efficient packing of these. So the real missing, and then it does have a leading 1 on the front here for that code. Because it can have a 0 at that. No, okay, so maybe we don't need to increase the index by 1. Let me have a think about why that's. Oh yes, because the so it's a special case, right? If not index, because otherwise it won't go in our loop, right? Right. So that's got that. So now we're adding on all of these pulses, and that's all fine and good. And then we start adding on. Oh, actually is because it's still doing the same thing. It's just getting the right simple procedural generation algorithm here is tricky. M3WP saying, is this relevant? I assume it isn't much different than on Windows, so you first need to decide on an alert server. Streamlabs is what I recommend. However, The other big one is stream elements. Once you're logged into one of those sites, you can make your custom alerts or mess around, blah, 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 blah. Chatty as a Twitch chat client. Oh, okay. Twitch chat client Linux. Chatty, yeah. Okay. Right, I'll have to have a look at that. Need to download the jar. I have to remember what my Twitch password is because it's just saved in the browser, right? That's right. Yeah, so if someone wants to have a look at a complete setup and then propose to me a complete solution, that would be fabulous. I'd love to hear that. Okay, so what I'm actually going to do, I think this might actually be a better way to do it. So we'll add one so that we don't have that problem with the 0, and then we'll take one off so that we can be in the first position if we need to. Yeah, that's a better way to do it. Now what we can do as well is we can trim all of, the trailing zeros off the end. So while offset and bit stream offs -1 is equal to 0, offs minus. What we actually need to do, because we've got our funky brackets in there, is we need to allow for that to be that, or a bracket, or the other bracket. Trim useless bits off the end. Right, so that's all looking good. So what we can see is we have here, we've got 8 codes that are just with the constant shift, and then for the 9th one, now why is it, this is going to, we just have to look at the logic for this generator, right? What we're expecting is not for it to then jump to having a longer code at that point. We actually want it to jump to this code next, and then it should be able to switch which of those bits it has on. So really, actually, in each of these sets, we actually want to vary between having it in each of the positions, but it can also be in, if you like, one position further along, which is having no ones in there. And the only time that we don't allow this is for the very first code, which we can fix by just doing another shift on the thing. So what we will do, we'll make it so that if in that 0th position will actually be with a 0. So we want to if digit Yeah. So, actually, I reckon that's the logic to do it. We'll soon find out. Yeah. So here we have, so that's the one that's all zero. So that's the one that we are not allowing and not supposed to be allowing. And it's still happening. And of course, it's all zeros, right? So the entire code has been trimmed off. So that's not what we want. Have to think about how we do that. Maybe that's the right way to do it. Yeah! Happy. Right. So we can have all of those positions in there. Now, what we haven't kind of covered is this one here with a nominal set of zeros at the end is actually the opposite, where we have a 0 here and a 1 here, because we're not doing variable length coding. So we will pad these out to all be the same length. But that's okay, so let's just make sure that this is still going through generating valid codes. The ordering that it's doing here is a little bit curious, because I'd really like it to produce the shortest codes first. Do I care? No, because they're fixed length. Maybe I do care. Because what we want is to know what the shortest length is that generates a certain number of codes. Yeah, Lighten23 says, I bet Emacs has an IRC mode. Oh, good grief, you're probably right. You're probably right. Emacs IRC client Twitch integration. Good grief. An Emacs package to interact with twitch.tv via Helm. In the spirit of doing as much as possible inside Emacs, this package provides a means of checking whether your favorite Twitch TV streamer is online using the Helm framework. It's as simple as metax helm-twitch. Yes, and you can join the streamer's Twitch chat directly through Emacs through ERC. Oh, and it contains a special live streamer mode that supports opening streams. Good grief. I'm going to have a look at that. That is a completely disgusting kind of thing. Yeah, Herdware says, I tried using Emacs, but it turns out I have too few fingers. So you know that in the early days, Emacs caused a whole pile of permanent RSI in a lot of the developers because they were using the Space Cadet keyboards. Minor diversion here, I'll show you the Space Cadet keyboard for those who haven't already seen them. And so this thing was a complete recipe for RSI. If I get that. So this is the keyboard that Emacs was designed with in mind. So we're used to having Shift and Control. Notably, it doesn't have Alt. But the meta key, this is where the meta key came from, right? So you go, okay, well, that's okay. I can kind of do those contortions. And kind of Commodore style, you've got front characters on there. You've got top characters. And then you've got, so there's top here to get the ones on the top. And then I think the front characters might have been the Greek characters. So there was a Greek meta key. And then there was super and hyper as well, just because they figured they didn't have enough meta keys already. Look, it'd be great for social media, right? Because you've got thumbs up and thumbs down. But if you imagine, so Emacs is famous for having combinations of the meta keys together with a single character here. So you end up contorting your hands to get to these meta keys a long way away and then pressing some key. And if you just try and do those maneuvers, you can feel your tendons stretching and complaining. And now imagine doing that, for hours a day for years. So this is why a bunch of those old timers from the Unix world have got the most horrendous RSI that you can imagine. So Vi was created in reaction to this in some regards, and so Vi doesn't cause RSI because it doesn't really need, other than shift and the occasional control, you don't need to use any extra meta keys. So anyway, historical thing apart. So heard we were saying, yes, Emacs used to be called 8 megs and continually swapping. Back when 8 megs of RAM was a lot of RAM. It was slow, and it's the Lisp language I actually find as a pain in the bum to program in. I'm not very good at it. But other people have made it do all manner of crazy things, so yes. Herdware says, yeah, Vim über alles. Yes, we can have the Vim theme song. But anyway, so we have this challenge that we want to turn the index numbers into the shortest possible sequences first, so that we can produce the sequences in... Defmego says, sorry, maybe you want to know, for me, your video comes around 250 milliseconds after the audio. Oh, okay. Leiden23 says it's fine. So if I do a sync clap, you can actually, everyone can kind of test whether it's in check. So I'll do a few of these. Yep. Video late. Yeah. Blame DHL Deft that the video arrives after the audio. Maybe Firefox. Okay, and Herdware also has a definite delay. Ah, interesting. Right. I'll try and move my lips then a quarter of a second before I make the sounds, perhaps. That would be quite an interesting skill to have, to ventriloquize your own video delay. Anyway, back to the thing. So we want to generate the shortest sequences first. So what we need to do is to have the order in which we kind of encode these digits. So the digit is where we place the bit in the thing, to have the shortest ones first. So I think actually all we have to do is we have to do the decades before we do the individual digits, right? Because I'm kind of turning them into multi-digit numbers with the sets of positions. So we need to do the division out, remember the values, and then process them in reverse order. Yeah, Herdware says like a cheesily dubbed Jackie Chan film. Exactly. Okay, so I think I know what we need to do then. So we need to int digit list max digits. Now this is okay actually in hardware as well, because we only probably need like 8 digits. In reality, I suspect it will actually be many fewer than that. Int digit count is 0, right? While index, so now we have to do the same logic for doing the digit stuff. Index equals index divided by positions. Digit list digit count plus plus is equal to our new digit, right? for int dignum is equal to digit count minus 1, dig num is greater than or equal to 0, dig num minus minus. So we go backwards through the digits. Int digit equals digit list dig num. Right, so that should get us our short sequences first. Haha, look, and now we've got a problem. The second, we've got a duplicate code. But, pleasingly, we are almost doing it in the right order. So let's try and figure out why that is doing that. So it's one digit, which is a 0. Yep, that's fine. And then this one we have the 8 and then we have the 0. Right, okay, so this is doing, it's getting the trimming happening from the end, isn't it? Because we're allowing the bit that doesn't show up to be, yeah, we're mishandling that. Let me have a think about that. So I'm going to take out this where we mess with the digit index. Right, so that's, yes, because it had that. Because what are we doing? So if the, let's have a look at, so these numbers here, yes, okay, so 0, that's right, yes, we have to add 1 to the, we do have to add 1 to the index, because otherwise it doesn't get triggered for the first one. That's all fine. And then, okay, so we were taking 1 away, so it goes 1, and that, when we put 8 on, so why did I want to take that out then? Because that, right, so that goes from 0, 7, well, this goes from, you know, counting to 7, and then we're going to 8. So that's because that's right, we have the check. Yeah, so when it's 8, we're not outputting the bit. Rather, we are, but we're outputting only zeros. So if I take the trimming off the end, we'll be able to see what's going on here better. Yep. Yes. So it trims it off the end. Now the trouble is that is identical to that code. It has the same prefix. Or rather, it's completely the same if we padded it out to a given width, right? Because there's only zeros following. So are we doing the digits in the right order then? Yeah, so we've reversed the order of the digits so that we're doing the decades first. The 0. This is trying to get the logic straight in my head so that we don't do that. Because we're happy actually to skip that first one. So in fact, actually we can say that if it's a 0 rather than the 8 is actually when we want to skip the bit. So that would mean that that would be all zeros, which is okay because we can skip that by adding one more to the index. Right, so we would do, if digit, we do that. Let's try that. Ah, yes, so what we need to do is we need one more. Sorry, one. Yeah, one. And is that? No, that's worse. Digit minus 1 because we're saying that the 0th digit. Okay. Almost, but not quite. Let's just put that back in there for a moment. So our issue, so the 1 is getting turned into that. So what we want to do is, if it's a 1, we want it to actually be here on the left, right? Instead. And if it's a 0, then we don't show it. So we need to have one less 0, so that gets that, that's all good. And then we are doing that. Ah, right, so now our problem is we've gone for 2 digits. So if the last digit we've put on as a 0, we actually don't need the last digit. Is actually what it is, right? You don't say, that 42 is, 0 hundreds and 42. If digit list digit count minus 1 is equal to 0, digit count minus minus. Eight, 0, right, so that's generating correctly there now, and we've produced the 2 zeros for the next one. 1 0. Yeah, no, see, that should be 8. So it's 8 ones and 1 10, so to speak. And so we're trimming that off, so we're saying that there's only 1 digit. But then the next one, this should actually have a 1 in this position. And it's not. The 1s aren't coming until later. So what have I screwed up in here? Yeah, so this is why I previously had a +1 on here. Is there, or is it just, is that what that's probably what I should be doing, right? Because the digit can take that many values. We divided it by that. But we still get 0 in the decades. I have to try and think about what the cause is there. Because that's just stupid. That works out that way. Because let's have a look at our codes. Because we add 2 to the code, right? So this first one that's doing this, so 7 gets turned into 9. So 9 divided by 8 plus 1 is 9. So index, but then we take 1 away at the beginning, don't we? Yes. If not digit count. We do that only on the first time around, I reckon. Yes. Right. That's looking better. And we can see that they're kind of now in a better order, but we still have this problem. We'd still like the 0, 1, 1 to happen. We actually... so what we need to do is have the sum of the digits should be minimized. So if it's... this is going to be a pig, I think, actually, in retrospect. It sounded like it should have been easy to do. And turns out it's not. Because what we want to do is, once we've got to the point of needing 2 digits, right? So we've got to this code here. We've got 1, and we've got the necessary number of zeros in between. And then, yep, we're going to do this code next. But the next code should actually be 0, 1, blah, 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 1. So we should be flipping the digits around before we increase the digits. So I have to think of a counter that produces that order. What a pain in the backside. Because otherwise I need to have a big fat ROM that has all of the different codes in it, and maybe that's actually unavoidable. Let's assume for the moment that we can solve this problem, right? So what we need to do is to come up with what are the sets of codes. We're abandoning the procedural generation. I'm just going to do it by hand for the moment. Can I? No, actually we can't, because if we want to vary these parameters to test, so we at least need to still stick with this. Now it's just, you guys have all been suspiciously silent, which makes me wonder whether I've actually got my chat window scrolled. I have. That's right, you've just been quiet. So we can produce these bit sequences. Yeah, a beep. And a tongue sticking out from a couple of people there. Excellent. Good. So you're still alive. So we can produce these sequences, and we can actually manually afterwards sort them by length, so that we know how many codes there are of a given length, and then we can work out what the minimum length is that gets us sufficient codes to meet the number of bits. That will work, and yes, we'll need to have a ROM if we go down that path, but we can at least do it. So we need to produce all of these codes up to 128, and we need to do the end trim, and we need to count how many bits they consume. So let's do that. Oop. And so we do want to trim the useless bits off the end. So let's... Okay, so that's producing our codes now. And you can see these codes they're purposely very sparse, because we have this requirement that we have the big gaps between the bits. So interesting, we actually only have to do 3 pulses to encode 128 different values. So that is actually really interesting, because naively we would have had 8 plus 128 positions. So it would have been like 132 long, and instead it's like less than 32 long. So it's only a quarter of the length. So this is what makes me think that we can get we can do better than what we've been doing by allowing those higher bit counts to go through. So let's do this. What we want to say, we want to count the length of it, right? Actually, we'll just go int len equals through len code. Right. Counts len plus plus. Int counts max was bit len, wasn't it? For int I equals 0, I less than max bit len. So we're just going to zero out our list here. Counts I is equal to 0, and then we'll say for int I equals 0, I is less than. We'll do the same thing again here. I plus plus. If counts I printf percent for d percent d sequences. So this is going to print out how many sequences of each length. I counts I. And I've left a percent sign out somewhere, haven't I? Yep. So we can see that on average they're about that long, but none of them is longer than 37 bits. And we can see that as they get longer, we get more possibilities in that given length. So we can say sum plus equal counts I int next power of 2. If you want to get to having more than 2, right? Int sum is equal to 0. If, well, actually it's while sum is greater than next power of 2, we want to show how many bits were needed to do that. Percent %d codes in percent %d ticks. So it's sum I is the length, next power of 2 times times right. And yes, because it's greater than or equal to. Right, and we're actually going to increase it. Let's actually go look, let's just for argument's sake, so I'm going to disable all of that stuff that's getting printed out while we generate them so that we don't have streams of rubbish going past. Right. And we can even hide those. Okay, so we can see that the number of ticks required to go up is not very many to encode more things. And let's, oops, int next bits is equal, that we 1 bit, right? Next bits plus plus. So we can actually see how many bits get encoded in how many things. And we can say how many ticks per bits equals percent point 1f ticks per bit. And we will see this goes, but this should decline as we go up. The number of ticks per bits goes down. But it will jump up on occasion because we start needing to have additional. So it will go up again. And the other thing, of course, is as these codes get longer, eventually there is a sweet spot that we pass. So the minimum is actually at 4. Now, of course, what we so this actually has taken into account that prefix that we have to have on the front as well. So when we were previously running it, 3 bits was the highest. Again, these numbers are completely out to lunch, right? Because we've lied about what the drive is capable of, just for doing this. So we should be able to get 4 bits up to being more efficient if we take into account this. So let's just see how this compares as well. So 3 bits is taking 10 ticks. So why is that saying 15? Because they should be equivalent. But let's actually go back to having realistic values in here. Yeah, so it's interesting. You can actually see that the minima is actually way out here. So that would be an annoyingly large ROM. We're probably not going to do that. But we can see for 3 bits we needed 65 ticks. So again, I need to find out why. Something is not right in the codes. They're too short. Because this is not adding on. We're going to have a look at what the codes are that are being generated again. And find out what's wrong here. Look, really long codes. Yeah, see, it's only shifting them by 1. It actually needs to shift them by quanta. Yeah, so this is overly optimistic at the moment, which we will fix. But that's okay. We are on the way. So when we generate our codes, so we have the quanta. So here we go, right. So we're doing a nested for loop. so that we're putting the right number in there. So they have to be that far apart. We just put the bit stream 1 in once. We don't have to stretch that out because it's just at a particular point in time, so long as the differences are greater. Okay, so let's have a look at that again. Right, so now we can see that there's 1, 2, 3, 4, 5, 6, 7, 8. Yes, so the code lengths are now changing appropriately. So we're expecting it'll be something like 87 for 2. So 1 bit's in 64 ticks. So how is it doing that? Because we have our so it's being a little bit clever in that we have the minimum gap length, which is exactly here, and then we have a 1 after it. We have the minimum gap length plus a quanta and the 1. So I think that's actually that's a real improvement. So that means that it should be 72 ticks for 2 bits. We should be 88 ticks for 3. And so somewhere we've stuffed up. We got those numbers out by 1, right? Which will be down here. Four sequences of length 64. That makes me suspicious, because there's some codes that are getting duplicated then. Yeah. Yes. That's bad. How are we going to filter these blackguards out? Okay. We are getting closer though, I think. So let's see what the digit set is for those that have that problem. So 64 has just a 1. Right. And then 8 has a 0 and then a 1. And so we do the 1 and then we do the 0. Okay, and this is going to be, yes, 1 and then the 0 and then the 0. So it's putting all zeros at the end of the code, and so then they're getting trimmed off again, right? Because we've reversed that order. So how do we fix that? Do we simply require that the very last digit has to be non-zero? We probably can. Because this is all with this where we're trying to suppress bits to get that extra bit of juice out of it. We could actually just disable the suppressing of the bits, and then all the codes will be a little bit longer on average. But we'll get a, it'll be a lower bound result then. But it would work. So I'm just going to try that for now. Well, that broke something, didn't it? Oh, but because it's producing a code which is all zeros. No, because that should be... Oh no, we've screwed something else up. Have I screwed up? GDB RLL optimize. Index to bit string, yeah. Right. It's just because it's overrunning. That still shouldn't. So if we're doing 2 and it's 1 digit, so that's a 2. Well, we can, let's just give us more space and see if that magically fixes it for the time being, and then we'll figure out what's going on. I'll fix that warning as well. Right. Cannot X. Right. Because it's not stack allocated, so that should totally be not a problem. Oh, what have I screwed up? Let's need to compile it again first. Because it should, yeah, so 1 digit, 1 digit. For num digit is equal to digit count. So the number of digits is 1. So it's 0, so that should be all fine. What are we? So our digit is 2. Oh. Right. So it's just infinite looping. Okay. And so we still have the problem that we had the gibberish. We're at least back to being in business. Line 23 is full of zeros. Yes, this is quite the issue. Okay, so let's try and think our way through this. So this is coming about because we've reversed the digit order. If I unreverse the digit order, because we're not trying to generate the codes in length order, right? So we can just go I think this should work because we strip the leading zeros off the number. Yeah, see, that's much better now. Yeah, one sequence of 64, blah, 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 so 2 bits. Yes, okay. Yay, right. So I can shut up a whole pile of that debugging again now, right? Where's that getting printed? There it is. Okay. And we'll get rid of that last bit of output so we get just a nice solid table for us. Okay. Right. Back in action. So, yeah, we see a decrease in the number of bits required, probably centering around here. And what we're seeing, so our numbers are now the same as what we have up there for the short lengths because we can't get any benefit. Minus 1, so I think I'm doing an extra minus 1 on here that I probably shouldn't be. That's okay. So it's actually interesting what we can see. So we're at 40, so here is at 30, so that should be 4/3 of that. Oh, this is looking a little bit more promising. So what we need to do is we need to write a table for how many bits are required at that given length, which we can actually we can calculate these on the fly in the table. So this is what we actually want to say is printf naive unary coding and then what we want to say is printf using multi-pulse coding, we'll call it just for argument's sake. So we want to produce a table that looks like this. Right, and bits per board we've clearly got defined somewhere up here, haven't we? Okay, we're doing it there, that's fine. So that's what our next bits is. Next bits, time per board. Where am I working that out? Okay, right. So that's our I, in fact. So time per board is equal to I and something is clearly wrong, right? Because this is not being that should equal to essentially that. How very sad. because we're multiplying by bits per board the whole time here, so that should be next bits. Right. So our peak is here. So using this code and assuming these properties of the drive, we should be able to get 1325 kilobits per second. So remember, a 3.5 inch high density disk is supposed to do 500. RLL and all of our other tricks are currently getting us to almost 1,000. And so this is letting us get some reasonable percentage again over that. So let me just, I'm going to record the RLL rate, right? Float RLL 27 rate. Because then we can compare these other codes. Right. You probably want 2 decimal places because it's got a fairly flat peak on it. Yes, that's a bit more honest, isn't it? So 1.37 times what we're getting with the RLL, which, if I do a quick calculation here, so we're currently getting 41 sectors with sector gaps. Times 1.37, that would get us up to 56 sectors per track, theoretically. And again, we might lose some bits and pieces here along the way. And we can get potentially 61 sectors per track, maybe even 62 sectors per track, if we do a MEGA style track at once. So that's getting pretty close to the 64 that we allowed. Now, there's questions as to how realistic these assumptions that we've made are, right? So we've said we think that the best rate that we can do is OX15 and a minimum quanta of 8. So yeah, it will be interesting to see how feasible that is. So let's now actually switch back to the MEGA65. Get a bit stream up. Get our floppy test program up. So what I'm wanting to do now, I need to step back down to track 0. Okay, so this is data rate 1.5. I'm just going to twiddle our knobs back down there. Just a big little and we then, the coding needs to be RLL, and we need to turn on all of our various correction factors. far. Okay, so that's the best that we were able to do previously with the RLL. Now, there was a problem here in that we can see that the peaks, if we're saying that the minimum quantity is 8, we're basically saying that every 8 640 horizontal pixels, so each character on the screen there, that we could tell a peak apart that close to each other. So clearly that doesn't actually work in practice. We can see here that the peaks are much wider. Now if we increase the time, there is a point at which they get narrower. And what we can see, of course, the longer the pulses are, so the pulses to the further to the right on this get a bit more spread out over time, because there's more slop, because more of the disk is rotated around. So it's possible that what I've listed there are overly optimistic in terms of what we can get. And in fact, I would say that at this particular setting, that we could probably only tell apart pulses that are 3 or 4 characters apart, which would be like 32 or 24, somewhere like that, apart. And in actual fact, these pulses actually are 24 pixels apart. So I've confused myself a little bit with the video. No, we're in H640. I'm just measuring the characters badly. So the center difference between these peaks should be 3 characters apart. Which, yeah, I guess they are. So as we come down in time, it's interesting. See, it's worse at that speed than at that speed. I wonder if there's something funny, like harmonics or something, with the drive electronics. There's all these rabbit holes you can go down, right, to try and optimize this further. But the other interesting thing, actually, if we keep pulling this down, is to try and work out the point at which, like, what is the shortest gap that we can reliably write and have it read. And so if we, because that's one of the 2 parameters that we need to know. And as I wind this further down, we can actually see that there is a hard wall on the left. Now I need to double check that I haven't put an artificial thing in the renderer for this, that it's skipping the first ones, because there's no point in showing them. So I'm just going to double check that. Yeah, drive speed control. That, yes, if you can make the drive spin faster, you can actually do better, because the magnetic signals actually behave better at higher speed, because there's an so the magnetic pickup is turning the magnetic signal into an electrical signal, and the faster the magnetic signal sweeps past, the larger the voltage peak, and the sharper it will be that it will produce. So let's just have a quick look back at floppy test. So it's gap histogram. So we've got our bins. And yeah, and so we're doing it all the way from 0, right? So this hard edge. Oh, so perhaps that sounds like what VHS takes advantage of, that the head spins faster than the tape speed. Yes, absolutely. And Beta does the same thing as well, right? So you have these, and then they do a helical scan on the tape. It's quite interesting how they do it without having to have the thing spin by at 47 bazillion miles an hour. So again, if we wind back, so we can see there's nothing being chopped off there. When we go to 15, we go to 14, it's still coming to the left. At 13, it's still coming to the left. At 12, it's still coming to the left. At 11, it's starting to get truncated. So I think the fundamental minimum gap is probably around at that 12 point. So that will be 3 times 12 in hex, so that's 3 times 18, which is 54 clock ticks times 25 microseconds is 1.35, sorry, 25 nanoseconds. So it's 1.35 microseconds, which is probably reasonable given that again, an HD drive is supposed to only have 2 microsecond minimum intervals. So yeah, and this might vary by drive electronics. In fact, it probably will. So it'll be interesting to quantify that out. So I think that's our fundamental minimum gap. Now, as we can see, the peaks are getting all completely smushed up as we get down to that. There are still, it's interesting, there are still definite peaks in there, which suggests that we can do some kind of right precompensation that might be able to fix those. If I take the right precompensation off that we do, again, we can actually see now that there's more peaks in there, and some of those are near to each other, particularly on the left hand side, because that's what right precomp fixes. And it will just be a question of where the that's bad, because if we get too close to the right precomp, it's going to do horrible things to the gap time. So and then we can do the pulse. So that's really interesting, the way that interacts now too. But interesting in ways that we can't really decode. So anyway, so that's I think our fundamental minimum gap time. But the trouble, as we see, is that the resolution on the peaks gets worse as we get to that point. So put out this thing I'm adjusting now moves the second peak from the left across to the right a bit as we push it down. So at that data rate, the peaks are quite wide, right? If we go slower, we reach a point where the peaks actually start getting really nice and narrow. And we can try turning off the right precompensation to see whether that's helping us or not. And we can actually see that that's interesting. If we don't do the right precompensation beyond a certain point, so a little bit of right precomp is helpful in this particular setting. We can see that really, when I put that up to a 1, the peaks are getting narrower. And so it's a question of finding the best one for that. Right, so this is actually looking quite nice in that we can imagine if we kept the peak on the left going no further left than that, so 1, 9. But we could now bring in the other peaks to be nearer to each other. We should be able to get those much nearer to each other. If I just freeze frame that for a moment so that we can actually see really how wide those are. So I reckon they're probably like the short ones are fine. The longer ones is where it starts to be a problem. So what this tells us is that actually having the trying to get more codes by skipping pulses in between is probably not that good a strategy. We're better to have pulses more regularly to keep the timing accurate. Because again, you've got drive spin variation and things, so you want to have enough pulses. Again, this is why the MFM and RLL codes are generated these ways. But we can actually see that that first peak, we can actually count the pixels, right? It's 1, 2, 3, maybe 4, 5, 6, 7 pixels wide, and the next one is what, 1, 2, 3, 4, 5, 6, 7, 8 pixels, and then it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pixels wide. So we can see that there is this problem as we go to the longer ones, but that we do have a really beautifully narrow peak there. So I might even actually see, can we, yeah, see, oops, I need to unfreeze it so that you can see. At this data rate, the peak is even narrower, right? Let me just fiddle with the right pre-comp to see where the optimum setting for that is. So that's like needle narrow, right? Again, if we freeze that for a moment, 1, 2, 3, 4, 5, 6 pixels wide. So we could probably tell apart, 8 or 10 clock tick wide bins to put things in. But that means that we have to have a minimum of 1B, not of 1.5. So we can start seeing, let's have a look at our so I'm going to put here this best RLL rate. Int best narrow rate 1B, we said, right? The rate which gives us the narrowest peak. Best rate. Oh, so here this is the RLL rate, so we want to do best RLL rate. Oops. So the positions is the minimum gap divided by the minimum. Okay, right. So this is going to quite change all of this. And what we see is that, depressingly, now there's only like a 10% gain to be had with what actually seems to be achievable on the disk. So this is really bizarre when you think about it, that we're trying to come up with schemes that can make use of longer codes and longer minimum pulses to get these really sharp peaks, and yet we don't seem to actually be able to get any real significant advantage over what this blasted RLL 2.7 code achieves. I find it really counterintuitive, because we can get much more precise timing resolution than what the RLL code can do. We can have more than, again, if we look at the diagram here, we could actually have more peaks than what the RLL code has and still tell them apart. So the more peaks, in theory, the more information we can convey. But I guess at some point, when the peaks are too far apart, this is where the problem is actually that the information density is dropping, right? Because you need to spend 8 ticks to communicate a gap of 8, whereas you only need 1 tick to communicate a gap of 1, so to speak. I'm possibly coming to the rather sad conclusion that the RLL 2.7 code is probably, like, if we're talking about within 10% of optimal, that there's probably little point trying to improve on it. So if I put the and then we're doing what was the magic value? So I think that's a little bit too fast. So that's looking reasonably well resolved at that point. We can try various things we might be able to clean it up a little bit better. M3W is saying would allow for drive error. I wonder what kind of equipment they had in devising the scheme. For the RLL 2.7 code, you mean? I think it was just clever mathematicians. Or information theorists to think about it. So, yeah. So my gut feeling as to what we're actually going to realistically be able to do, like, I think this rate 16 is pretty close to what should be reliable. And let's quickly answer this. Cool. So, yeah, my gut feeling is we're going to get somewhere around here. Like, we know that we can already do this kind of combination, right? And we can try and fiddle and see if... So this is weird. There's some funny interaction with the values of this third WPC field. Oh, yes, sorry, the screen is frozen. Yes. Yes. Thank you. Yes, sorry, just need to quickly respond here. Right. So my gut feeling is it's going to be somewhere around there. And it's interesting, it's like little changes to the data rate. So dropping it back to 1.7 really cleans it up quite a lot more. So M3WP is asking how many sectors? 39. So yes, at this setting, it's 39. And so this is actually one of those things, right? If I go back to data rate 1.6, it may still get the same number of sectors on, just because, well, it's getting one more, right? Because there's a 7 appearing on that bottom row. So the top row is 32 sectors worth, and then we've got another 8, so that would be 40 at that data rate. But to me, the peaks are probably sitting a little bit close. Although, maybe not. Maybe that's fine. If we push it out, then like they're really nicely resolved at that speed, which is getting us 38 sectors per track. And if we do a MEGA style track at once, then it's getting 42 sectors per track. Which, again, I mean, we're still we're talking about a lot of sectors on a track. Yes, right, yeah, 42 exactly. It says deft, and 38 sectors per track with gaps. I'm happy with, right, on the basis that is exactly double what a PC 1.44 meg floppy does. So it's in fact exactly the same as what an ED drive does. That's roughly 2.88 meg. Now, of course, this is on track 0. As we go to the higher track numbers, so if I step up, so I'll just keep stepping up tracks, and you can actually see as we go through that the signal integrity, how cleanly resolved the peaks are from one another, will start dropping off. So it's already looking a little bit scrappier there. Because what I would love to have 3.2 meg on a floppy, because then that's as much as what the FD4000 could do with an ED drive. But if it's not actually achievable, then it's not actually achievable. If we really wanted to try and cram more on, probably this is HD media, not DD media. DD media would not tolerate this kind of data density. So yeah, so we can see it's now getting appreciably messier. And as Marauder says, the HD media is actually easier to get hold of. Absolutely. Yeah, see, and like at about this point, that to me is looking too scrappy. It's interesting, it's still resolving the sectors. At least the sector headers without errors. At least a reasonable fraction of the time.
You're listening to Radio Parallax.
Let's jump all the way to the end of the disc. Right. So that's track 84. And it's still finding sector headers at least. But if I pop the time out a little bit, what? Right. So 1A is quite fine at that end of the disc, right? So that's getting us 33. It's interesting. Oops, we saw that some of these other data rates were really quite sad, but and again, it's quite sensitive to this shifting that second peak. What if I put that? Turn off the peak shift. You can see there that the second peak is quite left shifted, right? And so it's a trick of, oops, that's shifting it the wrong way. finding the values that work quite well and still let us resolve the peaks. So that's I think fine at that. So that's what, 34, 35, 36. I think we're gaps off, aren't we? So if we... No, we weren't. That was with... So this is with gaps off. So we can get 40 with gaps or 35 without on the innermost track. And if we then move back, we'll start getting better. So anyway, so I think whilst it's been a little bit frustrating that we haven't been able to find an amazing better encoding than RLL 2,7, yeah, I'm still doing 84 tracks. That will vary based on the drive as to whether they can tolerate it. We might trim back to 82. Almost every drive can do 82. Or we might even actually just be really conservative and actually go 80. So what we should probably do, I've got my, where's my floppy capacity test program. And some of these need updating, because now that we know, so that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yeah, so that's up to 20. And let's go back. Let's work out how many sectors we think we should be able to fit. And then we can run our automatic tester that tests how reliably it can actually read every sector from a track written in these styles. I really should just add a track 0 seek into this program, but anyway. So that's with gaps off, right? So we know we can go. That's to, yeah. So I think rate 16 is the lowest that we really want to go to, and so 16 gets us 40, so that's 16 hex, and I've put these tables in decimal order, right? So that's 22. So 22 gets us 40 with no gaps, right? 15 is looking complete cabbage with that correction, but with that, this is, it troubles me that the peak shifting thing has these weird periodicities where, like, you know, at some tracks odd numbers are good and even numbers are better. It's a bit weird. But as I say, it troubles me a little bit, which is why I think data rate 16 is probably better. That's better with less write pre-comp. That's more reliable actually, and less sensitive. So I think it's interacting with the write pre-comp. Yeah, still doing it to some extent. I'm actually inclined just to leave that last one off and leave the peak off center, because we can actually make the detector a little bit robust to that anyway. which case we can probably turn the right pre-comp up a bit more. Yeah, I think that's causing us more grief in the end. We can kind of tidy up one of the peaks, but then it upsets others of the peaks. So where there's kind of reliable double peaks and things, that says to me that we can actually do more sophisticated right pre-comp and probably correct for some of it. But anyway, so we're currently populating our table, right? So 40 with gaps and without gaps. Is 42 at rate 16. Yep, so at rate 17. Well, hang on. Is that 32? No, that was 44, wasn't it? Because we actually saw more of them come up. Yeah, 32 and 12 more is 44. Okay. The next rate up. So it's at least 41, 42. We call that 42 at that rate. Which is what I should do, so you can actually see what I'm looking at here, right? So I can see the which sectors are being found. So we've got 32 on the top row, and then we're looking at how many we get here on the second row. Okay, so let's one tick slower. So if it's going 0 to 7, so that's at least 8 more, so that's at least 40, but it might only be 40. I reckon we'll call that 40, and then we want to go one slower and see what that is. Marauder says, wasn't there a PC floppy stand of 2.88 meg? Yeah, so this is the ED drives that we're talking about. So the FD4000 from CMD had one of those in it, and the IBM PS2s, some of them had the 2.88 meg floppy drive. So I have one. I don't have any media for them. Now, what would be interesting would actually be to try and redo some of this stuff with a 2.88 meg drive, because I suspect that we can actually get more data on the disks using that drive, because it uses a different, the electronics are different and are able to tolerate shorter gaps. Hey, Amok. So I reckon that's 38 at that speed. Drop it down one more again. So we know we've got at least 36, because we can already see the... But it's having trouble. It's funny because it's... some of these speeds, they end up being quite metastable with the drawing of the graph. And so it will keep showing the same sectors. So one way that we can actually fix that is to temporarily stop the CPU and then restart it, and we should get a different little cluster of sectors showing. It's a bit of a pain in the bum, right, because it makes it a bit hard to actually estimate how many sectors we really have. Yeah, so Marauder says, I don't know about that without the widespread adoption of it. There's a whole lot of it. Yeah, so there's not many 2.88 drives out there, and they are really hard to find. So, yeah. Right, 36. How many are we going to get on this one? So we know it's at least... Oh, well, this is 36, definitely. Yep, so I reckon that's 36. So this is one is at least 35. Yep, so that's 35. Then that's also 35, so 1D. So that's 29, yep, so 35. We've got 33 at least. I think that probably is just 33. Oops, hang on. I didn't write it down properly. Again, we've got a bit of a resonance happening here. Just makes it a pain. But I probably could modify the code here so that it scans the sector numbers going past purely, like, rather than doing it once after it's drawn the graph, that it actually checks it more frequently, or that it basically watches it and watches to count the sector numbers go through in rapid succession, because it's randomly checking what's under the head at any point in time. So yeah, M3WP, you're asking where do you get the media? This is 2.88 media, you mean, or just regular HD media? HD media is still pretty easy to buy online, I think. ED media is you can also buy it online, and it's like outrageously expensive. I think it's, last I checked, it was like $5 or $6 a disc or something stupid. ED 2.88 megabyte media. Yeah, yeah. So someone is offering one disc for $15 US. an example. Here's someone else. Yeah, it looks like about $15 a disc is what people are charging. Which is nuts. So apparently the way they drive detects it, the index hole, you know, the capacity hole on the high density discs, it's basically shifted a little bit. And a SDC is how much? What do you mean SDC? Do you mean the floppy drive itself? You have to look on eBay. Sorry, an SD card. Yeah, that's right. Exactly. Exactly. SD card is much cheaper. Right, so we've got the blasted periodicity happening there. It's fine. So, right, now we're formatting again. So yeah, that's MFM, which is stinky. No. Anyway, it doesn't matter too much if we don't have all of these set perfectly, but what we need to do though is we need to go back to 16 and we need to turn gaps off. Oh no, the gaps are off now, so we had gaps. Oh, I don't know, confusing myself. I reckon I was writing down the numbers for gaps on versus gaps off. But anyway, so 32. Hey Marauder, no worries. Take care. We'll catch you next time. So it's 32. So that's 44. With gaps off. Right. Sorry. So we want with gaps on. Okay, let's see what we can see. So that's at least 38. That's at least 36, maybe more, 37. Looks like it's going to be 35 for that one, I reckon. $34. That one's 32, not 31. That'll do for now because we don't want to go any slower than that anyway. So now it's possible so bit interval we want to go from 0x16. We don't really want to check a very wide range. D6. I have to remember what the floppy test. Put it in RLL mode. D6AE needs to have 1 in it. Yes. Oops. RLL 2,7 encoding. Don't set track rate based on the track information block. We actually want to do that at the start of each track before we format it. Because what we do want to do after we've formatted the track re-enable auto data rate. So this is where it's going to read the track information block off the disk. And yeah. Need one of those FM radio auto tune buttons. I've missed something there. That's right. So let's floppy. No. So how was I need to yeah, it is there. Okay, make source tests floppy capacity. Right, let's see if we've got this happening. So this will try and read the sectors back at that data rate. The 3 characters on the top left of the screen are showing what sector, track and side is under the head. Now, as I say, I've fiddled with things with the floppy controller for all this stuff since then, so it's possible that we've balked something. Because it should be printing the sectors as it reads them. So read a sector. Let's see what we're doing. Going to make the border color go while we're doing this so that we can see where it's getting stuck. Yes, so it's waiting for the floppy drive to go ready, which is a bit weird. Reset the buffers and we command it to do a sector read. Right, it's all good. going to display the sector number on the char on the screen as well, so I can see if it. What have I screwed up? I find it hard to believe that that should be metastable. What I'm going to do, if peak OXD6A4 and OX80, so if the sector number matches what we're expecting, then I'm going to make it bump the border color. Your disc is spinning. What have I screwed up? What have I screwed up? Just have a character continually cycle. Because bizarrely, before that, unless it's running out of memory, there are some weird bugs with CC65 I find sometimes where the code generated. See, now it's, well, no, that's, maybe it's not happening in this particular instance. So we can see that the program is, oops, sorry, you can't see. So it's running. So the second character, that P, is the sector last seen under the floppy head. So that should be changing, which it's not. But it was before I put some of these other purely cosmetic debug changes in, right? Okay, now I'm confused because now it's back to exactly what it was before. And still not displaying anything. So oops. So I'm on the MEGA65 looking at the registers. So D6, A3, 4 and 5 are the most recent track sector side. And so that D6, A4 should be changing value all the time, which it's clearly not. So what have I balked up? So we format a side, actually let me, because some of these format things have changed. So floppy test. Right, so A4 is with pre-comp. So we want to just do, yes, I think that's, yeah, so no gaps is bit is the 8. Yes. Right, so that all looks like it should be working to me. Yeah. And yeah, well, no, it was right. Let me just switch back to the floppy test program and we'll see what's actually on track 0. Ah, the data rate might be getting set wrong. Because yeah, see, it's causing the same symptom here, but if I wind back the sector number, it should start moving again. Other than that, we found a way to crash the floppy controller. That would be slightly exciting too, in a really frustrating kind of way. Switch to RLL encoding. Okay, if I format it again, so there was something, the format of that track was being balked up. So what I'd need to do also probably is, it wouldn't have been setting the right pre-comp. So that will be a thing in there. So we'd say about that, I reckon, is about what's going to be good. Yeah, MGWP says, yeah, destroy the poor disk. Yeah. Fortunately not. So let's... There's our pre-comp values. Which we've changed where they live and how they work. I think that's... Yeah, so D6A7 will now read us back the encoding. Okay. Hey Gihaf, welcome along. Yeah, the magnetic media torturing is not going quite as well as hoped, but we're getting there. We've basically worked out that it's practically impossible to beat the RLL encoding, which is quite frustrating, but that's right. Right, so now we're actually getting something happening on the disk again. I'm just going to set this to start going from a slower data rate initially, just in case I've balked something up. Yes, right, so at that speed we're reading back the sectors reliably. So it might just be that 1.6 really is just a bit too aggressive to read a whole sector. And the reason for that being, of course, is that the sector headers are actually really short. And so the chance of having an error in one of those is much less than having an error in an entire sector. Right, so this is with, this must be with gaps turned off, I think, because it's reading 43 sectors at rate 23, which is 1.7. Yeah, so this is gaps off. Which is okay, because really what we're trying to do now is to quantify which data rate is doable. And so yes, as M3WP says, we're going to find out what the actual capacity is going to be realistically like. So we need to do a couple of these tests to work out what data rates on which tracks, and then we'll format a disk with those parameters, and then we'll use the readback test to basically see if it gets stuck on any sectors, or whether it's reading them all reliably, because that's kind of the other part of that. So we're up to track 11. So this program will drop back the speed by 1 each time if it doesn't read every sector without error from the track. Now, Minerail is saying the question was asked in Discord about will reliability and integrity of the data go down if we have a larger capacity, or will the sweet spot you find not affect reliability? We won't know until we test. And it's actually part of why I have made the track information block. Because I think actually experimenting with floppy craziness is actually going to be one of the things that people are going to have a bit of fun doing. Even if you don't actually use floppies to hold precious data. And I would still say the SD card is going to be a lot better for that than a floppy disk. But for people to be able to play around and try different disks and even potentially different floppy drive hardware and see what they can get on there. It's just one of many things that you can play and explore with on the MEGA65. And M3WP says, yeah, still interesting for limited capacity goals like comps. Yeah, so I think personally that there will, like demo comps on the MEGA65. I think that to me the most sensible format to have those is actually a single disk. What can you do in a single disk with the MEGA65? And then yes, it's up to you to try and find media and formats and things that can work really well with that. And show off as much craziness as you can cram onto one disk. Yeah, that's right, and having a good cruncher, right? Absolutely. Because yeah, with a decent cruncher, you should be able to get, 5, 6, 7, 8 megabytes worth of content on a single disk, right? And to do, nice background track loaders and all of that kind of stuff. I think there's stacks of scope for that. And I reckon after the big Christmas comp, we're giving away a MEGA65 production machine as the prize with Shalon. I reckon after that, we should actually organise a MEGA65 demo comp somewhere, somehow. Whether it's people going along to revision or something like that. So Internet is asking, ooh, have you leaked it? I thought it was completely open that a MEGA65 was the prize being offered for the for Shalon's Christmas competition. And of course, everyone, I presume, already knows that the pre-order opened 2 days ago, right? And that somewhere 600 or more units just see if I can get an update on how many units have been pre-ordered already. Where's my cursor gone? So I think everyone pretty much knows that the first 400 in the batch, that batch sold out. I think within about 6 hours. I was really actually pleasantly surprised. I thought, that the 400 will take 2 or 3 days to kind of to go through. But yeah, I was really pleasantly blown away, because we know the MEGA65 is not cheap, right? But it's never been about it being the cheapest machine. It's about it being the absolute most kick butt C65 recreation, C64, kind of day-to-day modern hardware and everything. So it should be really, really great. So Geehav is saying, yep, got my order confirmation in front of me printed out. And Amok is saying he should receive his JTAG USB adapter soon, and also received a mouster. I'm ready. Absolutely. And look, and it's that combination is just a joy, right? And I think M3WP, you were updating Solitaire to fix the random number generator, and I think have we tested Solitaire with the mouster yet? Because you haven't got one, because it won't work with the your R2 hardware. So I need to test that here at some point. But yeah, it's good. So we're up to track 40. We can actually see now that it's having to do multiple tries to read that. And we can actually see going back to track, which track was it? Track 34. It dropped back to rate 24. We might even, if you chuck me on Discord the latest D81, I'll chuck it on in a minute, and we'll do a bit of a test with the mouse. Oh yeah, that's right. Yeah, and Falco's got the mouse driver that we made with the hysteresis and all the rest of that nice stuff in there into GEOS to get a much smoother mouse experience. Because yeah, I was really happy actually with the mouse driver that we made for Solitaire on the MEGA65. It was just really nice, and doesn't have the jitter that the 1351 mice are a bit prone to doing because of the way that they get read. So I'm going to stop this. We're going to say that we can get to track 30 something. If anyone was watching with more eagle eyes than me, at which point it first dropped back to 40 sectors at rate 24, that would actually be really helpful, because I was too busy yakking away to pay enough attention. And I need another piece of scrap paper here so I can write this on. Yeah. I reckon it was about 34 or something. So what I'm going to do, I'm going to restart the program from track 30. I'll go for track 25 just to be really, really safe. So tracks 0 to something, we are at rate 23, which is 17, and so that's getting so track I'm going to restart it again, because it's possible that that's just balked on start. Because this program is basically held together with duct tape and goodness knows what, right? So no gaps is 42. We know that. And we've got the table there of what we're testing. Yeah, this is like any good prototyping software. Absolutely. Yep. So if you want to chuck me that D81 in Discord, if you haven't already just done so, M3WP, that would be fabulous, and I'll download that and we'll chuck it on in a minute. Oh, and throw me your the improved mod player as well. Okay. Downloady. And yeah, so if you want to throw me the mod player as well, your new one, that would be yeah, D81s are totally fine, right? Because I'll chuck them on, and that reads mod files off of the SD card directly, I think, doesn't it? So I need to chuck some .mod files on there. Okay, yep. Well, whatever version you like with, if you do a D81 with some mod files on the D81, that would be fantastic. And that'll be nice when we have the D65 disk images with this higher capacity, right? Because you'll be able to stack more mods in there. Sweet. Just downloading those now. Yeah, so you can see now it's starting to have trouble on that track. So I'm going to say that track 40 is a bit too far. I'm going to, yep, Gitcan, you just pointed out exactly the same thing. So I'm going to, for safety, we're going to say to track 35. So I'll just restart that. So we're going to go track 40 and we'll start at rate 18. So what's actually nice is the geometry of the disk means that most of the tracks actually can fit the full amount of data on, and that we actually then have smaller bands as we then have to drop the rate down a little bit by bit. So we can see we're getting nearly half the disk to track 35 at the highest rate, and then yeah, dropping it down a little bit after that. This is where I need to have a second MEGA65 set up on my bench and fed into the switcher, so we could be playing solitaire and watching and listening to the mod files in the background while this chugs away. You know, I reckon I could speed this program up by making it ask for the sectors in a different order. Because I'm formatting the tracks at the moment with one-to-one interleave. And so it means it reads the sector and then straight after, because there's no gaps in this format, right? So it has a few microseconds to basically be ready to read the next sector, but because it's printing some stuff out and stuff in the meantime, it misses it, and so it's a whole lap around, right? So it's taking 0.2 of a second, one revolution of the disk, to read every sector, which is why it's being a bit painfully slow. So who's going to enter something in the competition for the Christmas competition to try and win a Mega 65? Oh dear, M3WP says he can't do that. Very sad. Proud 7 saying maybe, but it seems like a difficult task for me. Yep. But I think it's one of those, even entering for the fun without needing to. Gearhouse is going to give it a go. Excellent. Yeah, whether or not you win or not, it's actually for the Mega 65 as a platform. It's actually fantastic just to see people making stuff for it, and that will really enthuse people as we go along as well. So yeah, it's really worthwhile. And actually, and I just want to say thank you to all you guys who actually are producing stuff already, because it does make a massive difference to getting other people excited about the platform. Yeah, so F3WP says it's great that we're starting to see people do things. So and your mod player and the Solitaire, they're already great things for people to be able to look at and go, oh yeah, there are things that I can do with the Mega 65 and things that you can spend time actually doing on the Mega 65, which is really nice. The applications as well as games and demos, I think is going to be really, really nice to have variety there. And who is it? Someone keeps talking about making an OGG Vorbis compressed music player, which I'd love to see running on the Mega 65, partly because if we go to the handheld, right, it'll be great to actually be able to play music on the go. So yeah, I think you're right, it's Deathy was going to have a look at that. So yeah, if I have to make minor changes to the hardware to add some extra feature that makes it a bit easier for him to do that, I'm actually quite happy to do that, because I think it's just going to rock if we get to that point of having the okay, so track 67 we lost some. Yep. So I'm going to call it to track 60 then, so that we're being not super conservative, but at least sensibly conservative. Okay, let's get that there. And thanks, Kitkanan, for keeping a close eye on that while I'm yabbering away, right? So at this data rate, with the gaps left out, we are fitting exactly double per track what a 1.44 meg fit. So we're doing exactly the ED data rate at the moment. So I think the last few tracks we're going to have to drop again, and it'll be a little bit below. But the first 3/4 of the disc, we're getting an average of an extra 3 sectors per track over what an ED disc does, which is really nice. The suspense. So yeah, someone can actually make an MP3 player. That would make me even happier as well, just because we know that MP3 is such a common format. But I think the math is harder on MP3 than on the OGG file format. I'm not sure. I haven't looked closely enough at it. Yeah, I think you're right, MP3, that there is M3WP. There is MP3s on the head, right? that there's a fixed point method for the Vorbis format, but for MP3 I think it does need floating point. I think you're right. Sorry, Mupe. Right. Cool. Okay, Gihav, how does the read speed compare to, say, an MEGA500 drive? Haha! Remember, when we cram more sectors on a track... right, sorry. So, Mute was saying, yes, it's only one W, it was for emphasis. Right. Don't mind me. So, if we fit 11 sectors on a track, which is what the Amiga did, right? That's 11 sectors in 0.2 of a second, because the drive is still spinning at 300 RPM. So it's 5.5 kilobytes in 0.2 of a second. So that's, it's close, call it 30 kilobytes a second between friends, right? So if we do a HD drive with, well, let's for argument's sake say it's an Amiga HD drive, right? So it's 22 sectors per track. Then we're talking at double that. We're talking at about 60 kilobytes a second. If we put 42 sectors per track, then it's double again. We can actually load from the blasted floppy drive at over 100 kilobytes a second across essentially every track. And I think we're not dropping any sectors, right? We're all the way out to track 82. And this data rate still seems to be pretty fine. Keith Canan says, yeah, depends on the interleave though to actually get that speed. Yeah, so to get that speed, you have to very carefully schedule where you put the data and the like. Okay, so that gets us to track 82. So we're going to call it to 79. And tracks 80 to 84, I'm going to say that data rate 1A will work for us, but I'm going to ignore that for the moment. So we're going to say that we have 29 tracks at the slowest rate. We've got, so this is where we use the MEGA65 as an on-screen calculator again, right? So we have tracks 0 to 35, so 35 take 0 plus 1, right? Because that's how many tracks it is. So it's 36 tracks times 42 sectors per track times 0.5 kilobytes per sector times 2 sides. So we can actually cancel that out because it's just that. So we get 1.5 meg just on the first 35 tracks. Then we've got tracks 60 to 36. We can do 36 plus 1. So there's another 25 tracks at 40 sectors per track. So that's another exactly 1 meg. Well, remember this is 1 floppy byte meg, right? Which is 1,000 kilobytes. So that's, oops, so it's 25 tracks, and then we've got 36 tracks at that rate, right? So then we've got 29 tracks out to track 79 at 18. So we have 1512 plus 1000 plus 522. So we are getting on the first 80 tracks 3.084 floppy megabytes. If we then add in those last 5 tracks at 36 sectors, that gets us another 180, which gets us to 3.214 megabytes. So we can just beat an FD4000 that had an ED drive with a DD drive, and yes, so I'm happy enough with that we'll probably basically call them 3.2 meg floppies. I think is not unfair. Right, so what's actually good with that is that basically says, Mupi saying 3.13. Did I do a typo in there? Yeah, that's right. Exactly. It's the Pi disk. Oh, you've calculated it as actual megabytes, right? Because we can. Yes, it's pretty close to pi, right? Yeah, so it's within 0.1% of pi. So if we can cram an extra sector on a track somewhere, we can get it right up to pi. So what we would need to do, it would need to be print pi times 1024. Yeah, so we only need an extra 3 oh wow, that would be so accurate, right? Because it's okay, that's right. We shall call them pi disks. So then they should just be .dpi files or something ridiculous, right? Yes, we can call. Yes, right. Okay, excellent. I think we can probably manage that. It's close enough that we can claim it. That's right. The laws of mathematics agree with us that we should be doing this, right? So excellent. Right. So 3.2 floppy megs or pi real megabytes. So it's the yes. Here we go. Paste this in the chat. Yeah, so Mupi is saying being a bit conservative on track timing could probably improve. Yeah, I think we could easily find the 3 kilobytes. But I mean, it's so statistically close anyway that it, you know, we're quite justified in doing that. So cool. So let's now, having decided that we're getting pi megabytes on a floppy disk, we need to transfer some things onto the. Oh, that's right. I need to update this to have the magic auto detection stuff. Because my laptop sits in a docking station now, and so it's on a different USB ID. So put M65. We need to make it so that it capitalizes files when it writes them as well. This would be good. And we'll have to speed this up because once we've got these the Pi disks, it's going to take 4 times as long to push a disk image across. We'll have to think about how we deal with that. Right. Yeah, so I need to copy the magic that I added into M65 that now actually pretty robustly detects what's going on with the USB devices. I need to add in there. So let's start with Solitaire. Right. So this is with the Pi. So I'm using a optical mouse with the Mouster adapter. And this is really nice. You know, like you can see that the mouse movement, it's not jumping and carrying on. What can I do? I can put that there. I can put. So this is where everyone will tell me what I can move around, right? What settings for Amiga detection in config? It's disabled. The Mouster is acting as a 1351. Oh, okay, we can get a keen clear. Someone will tell me. Yeah, so it might have. Well, see, I've got my Mouster configured as a 1351, so I don't need to have it on. If I had it on, it would cause grief. In fact. So, yeah. Yeah, I really love Solitaire on the Mega65. I think it's great to have it on there, and it just looks really nice. That yeah, you've done a great job with we've got the nice anti-alias graphics on the cards, and it was quite funny. It was quite a lot of work for us to do the corners to make them overlap. So they're actually done using the raster rewrite buffer to overlay the corners with the transparent outside edges of the corners over the card below. We do keep talking about having it so we can do raster rewrite buffer to actually move and drag the cards around or similar, or animate the moving of them, which would be cool. But look, as it is, it's just really, really nice. Like it is a totally playable and enjoyably playable version of Solitaire that I think people will, when they're tired and want to do something, that they just will. So that's really cool. So let's now have a look at your mod player, because I haven't had a look at. This will be the first time I've actually loaded your mod player, I think, because it's been tied up on everything else. Look at that, a file with mods. Now, to get audio playing, this is going to be. Do I have to press anything? F1, right? Okay. And then I type in the file name. Is that right? And you said you did tell me a delve.mod. Should that be that? Oh, you need to press. Okay. Hopefully that audio is coming through all right, because I don't have. Oh, hang on, let me just try this. Is that? Oh, okay, sorry, I'll put that back on. So we're doing acoustic audio pickup from the MEGA65. And if I'll turn off radio parallax for a moment. So for me, at least, there's a little tiny bit of crunchiness in it, but I'm not sure whether that's how I'm playing it through these crappy speakers, or whether it's really there. I'm just going to try and listen with the headphones. I think it might be clipping. So we're still there with the headphones. So I think you're saying the volume levels are hitting less than -3. Okay, use F12. Haha. Yeah, I reckon that's fixed it. Or nearly. Ooh. No, they're still in there. Oh, and the stereo mix on F14. Yeah. Don't know, but anyway, still, I love it. It looks really nice and cool. Having the vertical scrolling piece there is a really nice touch on it as well. And yeah, the color bars and everything, it's super. So the other disc has just got more mod files on it, is that right? Yeah, that's right. And if I will bring up the pre-order page inside Muncher, is that right? Asks Mindrail. Yeah, so not working on my version, I'm afraid. That would, once we had the browser working, that should be quite funny to have some of that kind of carry on going on. Cool. It's jukebox, but not enabled on the D81 version. That's right, because you've got a version that can read files directly from the SD card and work with that as well. So, yeah, that will be really cool as well. So, yeah, I think I'm going to wrap it up there. It's the family will be up and about soon if they're not already. Been great to have you all along, and as we kind of settled once and for all that I think we've got the capacity that we've got on the floppies is now basically set at pi megabytes, which is just really fun as well. And there's an Easter egg. Do you need to tell me somewhere off screen how? Yes, of course I'd love to see the Easter egg. You can tell me in a private message on Discord or something if you want. If you don't want people to know the key. And people will have to figure out how to find it themselves. Oh, okay. Right, so I will cut away for a moment so that you can't see what I'm typing. Oh, actually, it doesn't matter because you get to see it anyway, right? Oh, come on. What have I screwed up here? There we go. The topmost is Pepito, the mod itself, and then the various front end stuff. Oh, great! Asking about that. So, Press was asking about the border colors. Yeah. Yes, you can see it's using practically none of the CPU. So yeah, there's plenty of scope for us to do all manner of crazy things with this kind of thing, and make it yeah, look really good. So is that still, because it stopped playing, so we can't have the mod playing at the moment with that in there, is that right? Once we're in the Easter egg, there's no getting out, right? Where is there? Oh yes, we can. Yep. Cool. Yep. Actually, something I was going to try while we do this as well. Um, Let me try this. Dio. What I was trying to do is that there is you can do alpha blending of the sprites to the background. I was going to make the bouncing ball transparent over the user interface. So DO74, DO75 control that. So maybe, yeah, you have a squiz and see if you can make it work. It would be, and then that will, be really annoying for the Amiga folks, right? We can have it with transparency over there. So, so the funny pixels that aren't moving in the ball, that's just calculation that you need to do to resolve those, I presume, right? It's just the way that you're drawing the frames of the ball. So yeah, no, which is cool. I guess then if you want to really annoy the Amiga people, you can make the ball stretch and warp a little bit, given that you only need one frame per thing. But then we start saying, make a demo, which actually I would love. I reckon you'd be able to do a great job to make some nice MEGA65 demos to get people enthused and thinking about what's possible. You've got the music framework. And you've mucked around enough with the graphics, I think, to get an idea of some of what's possible to do. And we'd love for everyone to get involved with doing that. So, yeah. But anyway, I am going to sign off now. And, yeah, thanks again for tuning in. Hope it's been good fun. And, yeah, enjoy everything with the MEGA65 and have a good weekend. And look forward to your orders coming in as soon as Trends are able to get them manufactured and come through to you. So yeah, take care, and we'll see you around.